The driverless car simulation is an interactive educational tool designed to help students understand the principles of vector mathematics and their application in navigation and physics. By using the context of a driverless car navigating through a city grid, the simulation provides a hands on approach to learning about vectors, their components, and the mathematical operations involved in combining them. This simulation begins by introducing the concept of vector components. In a city designed on a grid, movement can only occur horizontally and vertically, not diagonally. To get from one point to another, the simplest approach is to move horizontally first and then vertically. These horizontal and vertical movements are the components of the overall motion, which can be described as a vector. The direct path from the starting point to the destination is known as the resultant vector. This vector is the sum of the horizontal and vertical components. The simulation helps students visualize this by allowing them to create vectors with specific horizontal and vertical components. For example, a vector called vector A with a horizontal component of +6 and a vertical component of 2 points to the right and upward. Its length, magnitude, and angle can be calculated and displayed. This simulation also allows students to add two vectors to understand how the car would move in two different directions, one after another. For instance, vector B might have a horizontal component of -2 and a vertical component of -5. The resultant motion is the sum of these two vectors. The order of addition does not matter. The car could first drive through vector A and then vector B, or vice versa. When adding two vectors, the components are added separately. For example, the horizontal components of vector A +6 and vector B -2 are added to get the resultant horizontal component, +4. Similarly, the vertical components of vector A and vector B -5 are added to get the resultant vertical component, -3. The simulation allows students to express vectors in two different ways: as components, horizontal and vertical, or as magnitude and direction. By using sliders, students can specify the magnitude and direction of a vector, and the program will automatically compute the horizontal and vertical components using trigonometry. Converting back and forth between the component representation and the magnitude direction representation is a useful skill for physics students and for understanding the navigation of a driverless car. The simulation helps students practice this conversion, reinforcing their understanding of vector mathematics. This simulation provides an interactive platform where students can actively engage with the concepts of vectors and their components. By adjusting the components and observing the resultant vectors, students can see the immediate effects of their changes, reinforcing their understanding through hands-on exploration. The visual nature of the simulation makes abstract concepts more tangible. Students can observe the vectors, their components, and the resultant motion in real time, helping them to grasp complex ideas more easily. The simulation offers immediate feedback, allowing students to see the results of their calculations and adjustments instantly. This helps correct misunderstandings quickly and reinforces learning through trial and error. The simulation is flexible, allowing students to explore a wide range of scenarios. Whether investigating the components of a single vector, adding two vectors, or converting between different representations of vectors, the simulation provides a comprehensive learning experience. The driverless car simulation is a valuable tool for teaching and learning about the principles of vector mathematics and their application in navigation and physics. By providing an interactive, visual, and flexible platform, it helps students understand the fundamental concepts of vector components, resultant vectors, and the mathematical operations involved in combining them. Whether used in a classroom setting or for individual study, this simulation can significantly enhance the learning experience and build a strong foundation in physics and mathematics. Through exploration and experimentation, students can gain a deeper appreciation for the complex and fascinating interactions between vectors and their real-world applications.